Okay, so this video is going to be looking at the last question in the long answer, the section B, question 3. As I've said before, I want you to make sure that you've really had a go at these questions before you look at the answers. Don't just go running for that crutch, running for that help. Make sure you've had a go. So, question 3. It's a percentage mass question. This is pretty common. So we have something, limestone, which contains some calcium carbonate, but not all, and we want to know how much of it is calcium carbonate. So we've weighed the original sample. We've added it to a particular volume and concentration of hydrochloric acid. And then we're saying that all the calcium carbonate is going to react with the acid. And we're taking the remaining solution, decanting, which means just pouring out the liquid and leaving any bits of solid behind, and making it up into a volume, taking out samples like we always do with a titration, and titrating it with sodium hydroxide to determine the amount of hydrochloric acid remaining, and we have a titer value of 22.6. So this is known as a back titration, and that is why there are two balanced equations at the bottom of the page. So what we mean by a back titration is when we can't directly, easily titrate to find the concentration of the thing we actually want to know about. So the last question we did in question 2, if you've done that one, was sodium carbonate. Sodium carbonate is soluble, so it's easy to take a solid sample of sodium carbonate, dissolve it into a volumetric flask, and take out samples and titrate. So far, this is what we know. This is what we did in the last question. So we can directly titrate sodium carbonate with acid to find out how much there is. Calcium carbonate is an insoluble solid. So if you add its acid, you can't make a solution. So we can't easily have an indicator to tell the end point. You may be thinking, well, we could just add a piece of solid, weigh it, and then just find out when the solid disappears, or how much acid it takes to make the solid disappear. This is in practice quite difficult because you'd be adding very small amounts of acid at a time, so the concentration would be low. It would be very challenging to do. And also because there are other things in the limestone that don't react with the acid, I'm never going to get rid of all the solid. So I can't do a titration of an insoluble solid. So what they've done instead is they've reacted the calcium carbonate with hydrochloric acid, shown in that equation there. Then they've taken leftover acid and titrated it. So here's a little diagram. I've even color-coded it. So the way that I color-coded it was I used blue for bases and red for acid, just to add a little extra something there. Obviously you wouldn't do that in an exam. Okay, so I've got a mass of solid which contains some calcium carbonate but not all. I've put it in acid. I've got a volume and a concentration written down with the acid. I've then written the equation to show how calcium carbonate and acid are linked together in terms of moles. And I've circled the acid because it's the acid that is going in the volumetric flask. There's no calcium carbonate left at this stage. The volumetric flask is 250 centimeters cubed. And I'm then going to take out 20 centimeters cubed, and it's been titrated with sodium hydroxide and burette. I've got volume and concentration, and again I've written the equation for sodium hydroxide and acid. So calcium carbonate, some of the calcium carbonate, or all of the calcium carbonates reacted with the acid, so I can work out moles for that, and at the end of the reaction we can then work out basically how much acid was left over. So we're going to start from the back end of the calculation as we normally do. So we start with the last pieces of information we got. We're going to work our way backwards through this picture. It's going to get a little bit crowded. I'm going to do a change of pen again and go for a green pen this time to do the calculations. So moles of sodium hydroxide. Typical titration calculation. I've got volume over 1,000 to make decimeter cubed times by moles per decimeter cubed gives me 2.26 times 10 to the minus 3 moles of sodium hydroxide. We know how to do those calculations, they're always worth a mark. So don't panic, you know how to work out number of moles from concentration. Moles of HCl is the same because they're 1 to 1, and I'm writing down, notice the volume, so that is the moles of HCl that's in that conical flask of 20 centimetre cubed volume. But just like the previous question, I haven't got 20 centimetre cubed in total, I have 250 centimetre cubed in my original sample that I took out to titrate from. So I'm going to do what I did before, actually in question 2, it's exactly the same idea. Dividing by 20 gives me how many in 1 centimetre cubed, timesing by 250 gives me how many moles there are in that whole volumetric flask of 250 centimetre cubed. So I've already worked out how many moles of acid, I'm going to write it back up there, are in that flask. So where did that acid come from? That's the acid that's left over when the acid in the beaker reacted with the calcium carbonate. If I want to know the amount of calcium carbonate, I need to know how many moles of acid was in the beaker originally. So it's another moles volume concentration question. 50 over 1,000 times 1 gives me 0.05 moles of acid. So that's how much there was in that beaker before I added the calcium carbonate and the limestone. And so now I can work out how much reacted in that equation with the calcium carbonate. So it's how many moles were in the beaker before, take away how many moles ended up in that 250 centimetre cubed volumetric flask. And that tells me that the amount of acid that reacted in the equation above with the calcium carbonate is 0.02175, that's my bad. So we're now going to write that down on a separate page because we've got very, very crowded here, so that we can get to our final answer of percentage calcium carbonate by mass in the sample. So far we've worked all the way back to how much acid reacted with the calcium carbonate that was in the sample. So moving on to the next page, which I'm hoping the video is going to do. There we go. It's always very difficult to record and then put your voice over the top. You can't remember how fast you did it. So moles of HCl, we had that from the last page. How much reacted was 0.02175 moles. And so moles of calcium carbonate, remember the balanced equation, it was 2 moles of acid for every 1 mole of calcium carbonate. So if I want moles of calcium carbonate, I divide my acid by 2 because of this part of the balanced equation here. So moles of calcium carbonate in that original sample that we popped into that beaker of acid is going to be 0.010875. And I'm not rounding up here because we're right in the middle of a calculation. If there were lots and lots of decimal places, I might round it up to say 4 sig figs, but I don't want to round up too much. So my mass, therefore, of calcium carbonate is going to be moles times the MR, so the MR is 100.1, and that gives me 1.0875 grams. This is good because this is smaller than the mass that's in the original sample. So the limestone sample that we had at the start of the question was 1.51 grams. So that means my percentage calcium carbonate is going to be the mass of calcium carbonate that I've got divided by the mass of the whole limestone sample times 100 to make it a percentage, and I get 72% as my final answer. So again, we would do a little bit of self-checking here. Does 72% sound reasonable? Yes, it does. Limestone is going to contain lots of calcium carbonate. It's the majority rock in things like limestone and marble. So I'm going to expect it to be a reasonably high percentage. So pay attention to what the question's asking you in a percentage mass situation. For example, again, if something said an impure sample of iron, you're going to expect your percentage to be high because you're telling you it's a sample of iron and there's just a few impurities. So if it says an impure sample of iron, I'd expect like 80–90% of it to be iron. If you got a calculation for an impure sample or for something like limestone and you found that it was 0.5%, well, hang on a minute. That isn't sensible. That's not a sample of limestone at all. If you had something like iron tablets, you might expect there to be less iron in that. Or if it was, for example, finding the percentage by mass of ammonium in a fertilizer, you expect less in there because there's lots of other things in those substances. But just think, is it a reasonable percentage? If it's more than 100, obviously it's not reasonable, but if it's very, very small, it's probably that you've done something wrong somewhere, probably forgotten 1,000, or more likely forgotten the dilution, forgotten this idea of making a big volume and then taking 20 out. Always remember that when you're doing a titration. Remember, again, any questions on this or any type of back titration, write them down, email them to cksciencetuition@gmail.com, and I'll try and answer those for you at the end of the week in the Q&A session.